Hey everyone, and welcome to another CTF Reddit video. Today we're going to be talking about JS in my BS. This was a pwn challenge as part of KalmarCTF. It was a pretty crazy challenge where we're going to be injecting some shellcode into a boot sector, and this boot sector has a JavaScript engine written in it, which is pretty impressive because boot sectors are only 512 bytes. But we're going to inject some shellcode that will then read in a additional sector which contains the flag, and then we have to leak the flag. The actual exploitation of this binary really wasn't that difficult. We're just injecting some shellcode. The difficulty of this challenge was just getting set up and really understanding what it is you're supposed to be doing. I think most people aren't really used to these sort of operating system challenges, myself included. But like I said, if you know what you're doing, really not a bad challenge. It's just getting set up can be a little bit confusing. But yeah, let's get started. So for this, they give us some examples of what the JavaScript engine looks like. So we can do addition, we can do equals, there's some sort of symbol table, there's this L function that kind of looks like a print function. It says there's multiple steps. We're given a netcat port and a download file. If we go to the download files, there's a bunch of different files. One of them is the Docker file, so we can see it's running on Ubuntu 22.04. It's going to install a bunch of stuff, copy a bunch of stuff over, and then it's going to run this run.shell. If we look at run.shell, we can see it's doing some copy operation with this boot.js bin file, which was included in the downloads, and then it's going to call QEMU. There's some other files, but they're not too important. So we can run this file, run.shell. We get that interpreter prompt here, and we can do what the demo says. So a is equal to 1 plus 1. Cool. B is equal to, oops, I put a space in there. You can't do backspaces or anything. Like I said, this bootloader is running in, or this JavaScript engine is running in 512 bytes, so it's very small. So a lot of things are a little bit wonky. For example, you can't use backspaces. So we'll do B equals 2 plus 2, and then L is equal to A plus B. So we can load it up in Ghidra. There were a couple of tricks for loading it in Ghidra. First is when we go to language, we want to select or filter for real mode. And that'll work. Then we want to go to the memory segment, memory map. We're going to click move, and we want to move it to a new start address of 7C. This is where boot sectors are loaded into, so we'll do that. And we can also see by default Ghidra isn't decompiling anything, but if you just select on one of these lines, you can click D for decompile, and it'll decompile all the lines. And it doesn't get everything. You have to click D a couple times through here. We can see there's a little symbol table here, and this stuff is also part of the symbol table. If you didn't load it into, so we did that memory mapping where we moved up the address. If you don't do that, it's not the end of the world, it's still fine, but there's a couple things that won't make sense. For example, there's this move instruction where we're moving OX7CDA into SI. We can see that if it wasn't there, this would be like 0CDA, so they don't quite line up, and so we wouldn't get these references, but otherwise it worked fine. So I'm going to skip over doing most of the reversing. It's pretty standard assembly. We can see here we have like an add function. It's going to pop off some value. It's going to add them. Really, this code is just going to loop through character by character. It's going to read your input, and it's going to do the addition, the subtraction, and it's going to assign variables. But there are two things that are very interesting that'll be necessary for the exploit. First is the symbol table, which I'll come back to. And the next is at the very end of the boot.js bin file, we'll see that most of these were A's, and here we have a 55H and an AAH. And so these 2 bytes are the magic bytes that say this is the end of the sector, and they should be bytes 510 and 511 using 0 indexing. And so, like I said, these are the magic bytes that say this, hey, this is the end, and I think it's also a sanity check while it's being loaded in. After that, we have the Kalmar flag. So this flag is not included in the initial 512 bytes. And so that means when we get execution and we inject our shellcode, we're going to have to load in the second section. Cool. So we have our goal. We need somehow to get execution, and then we need to load in a second section. And there's no code in the existing binary to load in sections, so we're going to have to inject our own shellcode. So then in the symbol table, we're just going to look at it real quick, and then we'll jump into GDB. Here's that L. So we were using L to print stuff. And so in the symbol table, it's used for two different things. One is storing variables, and the other is storing functions. And so here we have, by default, one function defined, L, and if it's a function, it's going to be 1 byte for the function name, and then 2 bytes for the address. So we can see the L function will jump here, and if you just double click this is one of those print functions. So we can also use this for storing symbols. So earlier we did a is equal to 1 plus 1. When we do that, this will be assigned to lowercase a, and then the next 2 bytes will be 0 and 2. So we have a pretty powerful primitive that's because it's being used for two different things. So we could then define a symbol such as a, and then say a is a function, and that would allow us to jump to address 2. So right off the bat, we have an arbitrary jump gadget, which is very powerful. Like I said, there's no existing shellcode in here that loads additional sections, so we're going to have to inject our own shellcode. But it's really not too bad, since we're allowed to put whatever we want in here, and then we also have a gadget to jump anywhere. We're able to inject our own shellcode into here. So if we load this into GDB, let's go back here. We're going to do a tmux. We're going to split. One thing to note is there's this file that really just saves the day. This GDB init real mode file. You can find it if you just Google for it right here. What this will do is it'll pretty print everything because pwn debug doesn't work in 16-bit mode. And it'll make everything so much easier. Also, in our run script, we need to change a couple of things. So by default, the run script doesn't allow debugging, but if you add a _s and an uppercase S to the QEMU system, which this will do is, I get them mixed up, but one says launch the debugger port, so this will set up a debugger on localhost 1234, and the other one says wait for the debugger before you execute. Then I have a debug file. So this is a file I made, so it's going to launch GDB. It's going to include that real mode thing. Again, it makes everything so much cleaner. I highly recommend using it. We're going to set the architecture to this. We're going to do a remote debugging on local 1234, which is set up by QEMU for us. And then I have two little break statements that'll come in handy later. So we can run this. So we're going to do run, jump into the other terminal, debug. It's going very slow. Oh, it broke. Oh, by default, I have pwn debug enabled. So if you run into this weird issue, you need to disable that. So we're going to go to GDB init, insert comment, and let me rerun it just in case. There we go. Looks a little bit messy. Let me see how big I can make this without it being terrible. Okay, hopefully that's viewable. Like I said, this that handy file, that real mode registers.txt thing, what that is doing is it's printing out the assembly where we are. It's also showing us the registers. It's very similar to pwn debug. So first, it stopped right at the start of execution. So we're going to continue, and let's break at maybe we'll break here. So 7C, 7A. Break at 7C, 7A. Oh, actually, and we need an OX. Cool. And we'll hit continue. And we go back over here. So let's do A is equal to 1 plus 1. B is equal to, let's say, 7. And let's print out B. So you can see a breakpoint was triggered. Then, and it's triggered on 7C, 7A. If we take a look at what that is, that was where this was called. So we called the list function, it jumped here, and we're about to do all the printing of the value there. Instead, let's actually inspect the symbol table. So the symbol table is located here. X, we're gonna look at 20 bytes at that address. Cool, actually, and let's look at characters. Make it a little bit, we'll do bytes. Weird. This is not the best. I wonder if there's a better way to do this. But anyways, we can see a couple values. So we assigned A equal to 2 and B is equal to 7. So this is the ASCII for A, and it's assigned value 2. Next is a 0 because it's 16-bit little Indian, so the 2 will come first. Next is B. We assigned it the value 7, and it's little Indian, so it's 16 bits, so we get 2 of them, and it's just the value 7. And then the rest are just A's. So pretty crazy. So we can assign variables and values. And this is how we're going to inject shellcode. And like I said, there was also, we're also able to, I think I got this address wrong. Yeah, this is, we actually want a DA. Here we go, a little bit better. This is the L, and this was that address it jumps to actually do the printing. So we have L, a jump address, A, the value 2, B, the value 7, and then the rest are unset. But we're allowed to assign any symbol we want here, so we can start assigning crazy symbols that correspond to shellcode. To do that, we need to generate some shellcode. So to generate shellcode, I used nasm. So I wrote this little file, and this is it. And so we need shellcode, like I said, that'll load in the second section. So we're going to tell the assembler that we want 16-bit mode. I don't actually think we need this, but I copied this from some other bootloading code. I defined a label called load second stage. At the very end of this section, we're calling interrupt 13. This is the interrupt that does the disk operations, and you can find this, I think it's called osdev.org or something like that. Yeah. This wiki has a whole bunch of stuff for getting started. I read a couple articles on like the boot symbol, the boot sequence this way. It talks a little bit about like, you're going to be loaded into OX7, 7CO. But anyways, this will have a table of interrupts, and it'll kind of tell you how to set it up. During the CTF, I actually did not solve it. I was missing this single line, which is why I didn't solve it. Apparently you need to set disk to OX80, and the code that I was using did not do that, and I don't really know what I'm doing, so I had to wait, and I saw someone else's solution. I saw that I was missing this OX80 line. But anyways, we're loading in the second stage to memory, so we're going to set, and that's where this 2 comes from. We're going to load that into AH. Like I said, you just copy this code from online somewhere. There's a lot of different places have to do this. The number of sectors to read, we're going to read in one sector. The cylinders, the heads, the sector number. I think these are all carryovers from loading from disk. Then we need to decide where we're going to load it into. And so we're going to load it into 7E. So right now we're using 7C. And it's 512 bytes, so that's 2 256s. So that's 7C, D, and now E. So 7E. Again, I don't know what this disk is, but we need to specify the disk. And then the disk IO interrupt. Cool. Once we've done that, it'll be loaded into memory. And so this is the code for printing it out of memory. So we're going to load the address of where we loaded the second section into, here. This is related to how you print. If you look at the decompiled code, you'll see this. They move this into DX, and then they call out AL DX, and that's how they print characters, so I just copy that over. Then we have this print loop, so this is an assembly instruction for loading a byte, and it'll also increment SI, which is our pointer to which character we're printing. So it'll load that, it'll increment it, and it'll set the context into AL. So we'll load that byte, set it into AL, print it, we'll jump to the top, load the next byte, print it, jump back, load the next byte, print it. And then I added a couple of nops so that as we look at the solve script, we have to 3-byte align things. And so these nops just make sure that we can 3-byte align stuff. And that was the shellcode. So to actually compile the shellcode, I used a tool called nasm, which is a assembler. So we're doing nasm, compile the shellcode, and put it into a bin file, and then I just print it out. And I say shellcode.bin. So we can run that. Let me close. We'll do make shellcode. What was it called? Shellcode dump. Oh, I don't have nasm installed. Whoops. Apt install nasm. Cool. Now we can run it again. So it was make, what do we call it? Shellcode dump. Cool. And here's our shellcode. So now we need to write a solve script which will correctly set the right symbols and values so that shellcode exists somewhere. So this is the solve script. It's pretty messy. But we're going to use pwn tools, same as always. We're going to start a process. So instead of typing out all the keymu commands, I just use the existing run script. And I say shell is equal to true. Doing the standard tmux stuff. I sleep for a second. I tried to get the pwn tools to launch GDB within the script, but it just wasn't working well. From there, we're going to receive line just to get that cursor. There's the change value. I'm not actually using this. I'll talk about this in a bit, but thankfully we don't have to use that anymore. And I don't think I need that, but I'll keep it. All right. So one complication when running this is we need to sometimes set values that are huge, but we're not actually allowed to set huge values in the interpreter. And to show what I mean by that is, let's do run. We can make this bigger again. Let me actually clear and reset. So we can do a is equal to 1, for example. But if I do a is equal to 1, 1, and we do list a, we'll see it's only equal to 1. So we're only allowed to assign a single digit to a variable. So the biggest one we could do is 9. But there is a couple of little tricks. We can do operations. So we could do 1 minus 2. Then we list a. Oh no. List a. And we can see it's FFFF. So we can get very large values and very small values. I think there's a bunch of different things you can do. I saw someone solve script and they just did, which is what I was originally doing. You can do as many adds as you want. So you could do this. You still have to get up to 2 to the 16, which can take a while and be very long statements, but that's one solution. What I ended up doing was just kind of a binary addition sort of thing. So I defined a is equal to 1. Then I said b is equal to a plus a. Then I said c is equal to b plus b. Then d is equal to c plus c. And I go all the way for 16 characters. And then if we look at d, we can see it's 8. So if we did e is equal to d plus d, we would know that e is then 16 in hex, which is 10. And you'll be able to get each one of those letters represents a single bit. Then I take the shellcode I want to inject, and I just do that little bit masking. And I see if this bit is set. So let's say I want to generate my next payload is equal to q is equal to, I don't know, some bits. If maybe I need the a bit, the c bit, the d bit, and the e bit, I just do something like this, and then I can do lq, and we can see it's 1d. And so that's how I was able to inject shellcode. And you also have to be careful with that initial character too. Back to the solve script. Like I said, there's a lot to this, but at the end of the day, it really wasn't terrible. I think it's a lot of little technical details. But anyways, this was that shellcode. So I split it into chunks of 3 bytes apiece. Because you're going to do a equals and then a value. So instead of saying, 41 for capital A, we're going to say whatever character before is equal to, and then we need to set it to this value. And like I said, I'm going to do that bit masking where I separate all the variables into a single bit, and then I'm just going to add them together. So we're going to split through this. We're going to assign a B4 variable, an O1 variable, a B6 variable, an O2 variable, a 7.2, blah, blah, blah. And we're going to set them to those values. And if we do it correctly, this shellcode should exist within memory. And so like I said, I'm just splitting it out. I was kind of lazy. Instead of actually like decoding it and unpacking it, I just take the hex characters. So hex character 4523. So this is 4523, just because of the little endianness and stuff. Then I parse it as hex, and then I have this set value function. Again, this is all just kind of operational details, but I have set values. This is where I define all those bits. So it's probably a smarter way to do this, but so I have a is equal to 1, b is equal to 2, j is equal to 512, all the way to p down there. And then as I go through the values, I just see, hey, I go from the reverse order and I say, hey, can this value fit? If it can, add that value on and then subtract it from the value I'm trying to get. And at the very end, I assign those large, bit adding statements. And cool. And then the very last stage is we need a jump instruction that'll jump to our shellcode. And so here is what I do is I assign the variable x for execute. I assign it this value, 7DOD. You find this value by looking in GDB, and you see where your shellcode actually starts. And so I'll do that in a second, but I was able to see that the shellcode starts at this line. So I set x to here, and then all you have to do after that is just send XO, and your shellcode will execute. So if we look at it in GDB, let's go back to run. we need the debugger to be re-enabled. I don't think we need to do anything in here. Get rid of this. Hopefully it should break right before. We'll save, go back here, cancel, we'll do a tmux. We'll split in tmux, we'll go back, we'll do python 3 solve, then we'll do debug, debug.shell. It's printing everything out. I might have to make it a little bit smaller, but maybe not. We'll do a continue. So that's this is the shellcode actually injecting. Sorry, it is the Python script injecting the shellcode. So this is the first 3 bytes of shellcode. It's going to parse it. It's going to see its label this with a hex byte, and it's going to set those values. Cool. So at this point, did we jump to shellcode? Yeah, we already jumped to shellcode. But let's take a look at what the shellcode looks like. So I'm going to print out the symbol table. Examine 20x at that address. All right, so the symbol table originally was just, let's do 20 bytes. And I have to make this just a little bit smaller. Cool. And did I go to the right one? Of course not. We want this one. And OX. Cool. So we have 7C. Oh, I think we reused L, which is interesting. Oh yeah. So first thing we had to do was we assigned A, B, C, D, E, F, G to all of those individual bits for the full 16 bits. So we can see this is L is equal to 8. I guess this is a jump address, I think. This is A is equal to 1. 2, B is equal to 2. C is equal to 4. D is equal to 8. And it keeps going. Eventually, we'll get to the start of the shellcode, which I think is here. So the last one would be 0080, which makes sense. That is the highest bit set in Little Endian. And so here we have the B4, which I believe is the start of shellcode. Yep, B402BO, B402BO. So at this address, following it, our shellcode is loaded in all the way to here. Actually, one less, but all the way to here, I think. Cool. And so the only thing left is we count what this offset is. So this is 7DOA is right here. So that would be BCD. So 7DOD is at the start of our shellcode. So we need to add another instruction that jumps there. And I have it right here. You can see 78OD, or no, 7DOD. So this is X 7DOD. So now when we call the X command, it'll jump here and start executing shellcode. You might have saw that the shellcode's already executing. So if we do single instruction, oh, it's very slow. But this is what that nasm script was doing. So we're setting up the registers. We'll do a single step, single step, single step. We're just assigning registers, single step. It doesn't always get this stuff right. GDB thinks we're using EBX, but really we're using 2 smaller registers. There's probably a way to set the architecture correctly. Even though I am doing an architecture set, I'm not really sure what's going wrong. But we'll do another jump and eventually it'll split it out correctly. And now it's going to move OX into DL, the thing that I was missing during the CTF. Now it's going to do that interrupt call. So this is now we're going to load the second sector. It jumped somewhere. I don't know where it jumped to. I'm guessing this is part of, when we call QEMU, there's like a -L boot folder. I'm guessing this is in the bootloader, but we can continue to until we get back into our shellcode because I added another break statement there. Again, it's a little bit wrong or confused about what is going down over here, but we'll do a single instruction, single instruction. Now we're going to load that byte. So we're going to load our first byte of the flag in, which is exciting. Then we're going to print it, and we get a K, which is for Kalmar. So we can just keep jumping, and if we keep hitting enter, it'll print out the flag, Kalmar. And that was it. So basically you jump that, you can wrap all that together, get rid of the debugger, and yeah, you'll be able to print the flag on remote. There's also they do a hash check, but that's easy to do. But yeah, a pretty crazy challenge. Like I said, we're using QEMU. The challenge author gave us a bootbin.js, which is a JS interpreter running in a 512-byte boot sector. We were able to use Ghidra to reverse the binary, figure out where that symbol table was located. We found out that it had a jump instruction or jump gadget where we could jump to arbitrary locations. We found a way by abusing the symbols lookup table to inject shellcode. Then we use that to jump to the shellcode. From there, we're able to use the interrupts to load a second section from disk into our boot sector. And then from there, we did a little print loop so that we could print out the flag. Overall, the CTF was a lot of fun, so thanks to the challenge author, Newbie Edge, and also to Kalmar for hosting. I'll see you at the next CTF. Bye.